this time. For the MTech students, what I'm planning to do is the MSP 356 would have all the MS and PhD students, as same as last time. Those of you who recollect. But now instead of splitting the MTechs between two rooms, I'm just going to require that they all sit in one room. 355, all the MTech students. So we are now moving away from the official seating arrangement, which has some of the MTech students in 240. So I think in the 355 is very much crowded, so we can just add 10 students to that. So I require all MTech students to please come to 355 and don't wait in 245 your question day. Because here it says MTech CH15M is equal to 23 and must be 240. So I request all those students to also come to 355 and find a seat there. Already questions on the seating arrangement. So depend you will sit in the HOD's office. That's as before. So then regarding the quiz, it will be again closed books and notes. It will be a mixture of analytical and numerical. Because analytical is not completely possible to avoid. It will be heavily based on numerical numbers. So you have to get the numbers right. So you cannot say that I made a calculation mistake. That means the marks won't be given. Another thing, there will be an explicit statement in the question paper that if you give numbers without any units, I cannot give any marks. Because without units, the numbers don't make any sense. So every quantity, especially the final answers, maybe intermediate steps you can ignore the units, but finally when you give the answer, let's say I ask you for the pressure or volume, saturated volume or fluidity, you should give the units. And sometimes I might say that you give the pressure in Pascal or in bar or atmosphere. Even then, you have to clearly give the pressure in the required units and put the units clearly. So without the units, the numbers really can mean anything. Right? So conversion factors, some of them you should know how to convert from meter to although there will be very little of that. Joule to kilojoule, kilomole to mole, minimum you should know. Pressure units you should be very clear. 1 bar, I cannot be giving everything all the time. 10⁵ Pascal and so on. And the different units, and then you also have megapascal, kilopascal and so on. So all those units you should know. I hope this is correct. And is this correct? And so 1 atmosphere is of course slightly different. I think 1.0132 into 10⁵ Pascal. And then you also have megapascal, kilopascal, bar. I have written kilo, bar and so on. So all that I can't think of any other. So units of R is at least known 1 unit is joule per. Sometimes I may give these, but if I forget, these are basic quantities you should remember. Pressure units, we've looked at different units. More or less volume, we always looked at meter per mole. More likely to stick to that. Pressure, it depends. So if you don't want to give a big number, into 10⁶, I may just convert it to bar and give it. And so you should know how to actually use it in the calculation. You should know that if everything has to convert Newton per meter square, it is Pascal. 1 Pascal is actually 1 Pascal is 1 Newton per. It's a basic unit. So you should know all this very clearly. You can't be looking at the question paper for this. You should know this. It will also facilitate your quickness in calculation. Of course, all definitions you should know. Basic equations and definitions you should know. Fugacity of a component in a mixture, partial molar property, right? Gibbs gives equations and now you don't have to remember, right? We'll give that. Partial molar property, basic definition you should know. Ui, dm, du by, this is how we introduce, so that comes in a definition. However, the expression in terms of the mole fraction, that you don't have to remember. Namely u plus du by dzi and so on. So definition, because it also differs for the, so those if they are required, either I may ask you to derive it, or if they are required, I will just give those equations to you. So, but basic, this would come under definition. I can't similarly properties of ideal gas mixture. At least one definition you should know, right? Chemical potential of components, how it is defined for an ideal gas mixture, for an ideal solution. All of that you should know. Basic definitions and introduction to certain properties of the ideal substances. At least one of them you should know. How they are introduced. So we defined the ideal gas mixture as mu I IgM equal to mu I Ig plus RT log by I. So that you should know, that comes in the definition. Right? So are there any questions on what you should come prepared for the quiz? Portions, as I said, will be everything we have covered until phase equilibrium, but excluding phase equilibrium calculations for mixtures, which we have just started to cover. The application of the phase rules to interpreting phase diagram, that is part of the quiz 2 portion. So, anything else? So we won't meet again until the quiz, so just want to make sure that everybody is looking clear. Maybe you have to bring a calculator this time. There will be a lot of numbers and you might have to do that fairly rapidly because time might be of the essence. You have to do it correctly also. Numbers are wrong. They give you the formula and all you have to do is to substitute, and you make a mistake and then you cannot really expect me to give any points. So you have to do the calculations correctly. Now we continue with what we were discussing yesterday, namely the BAE algorithm. And we introduced 4 basic problems. One is the Raoult pressure calculation, another is the new pressure, and third is the Raoult temperature, and fourth is the Raoult new temperature. We will see what this means, what is specified and what is to be calculated. C variable, degree of freedom is C. There are 2 C variables. Okay. So C variables have to be specified, and you have to show how to determine the others. Now we saw the case of the, now we get into models. This is common for all multi-component BAE. Right? Now we get into actual calculation. So we start with the simplest model, which treats the vapor phase as an ideal gas mixture, right? And the liquid phase is approximately the ideal solution. So it's not exactly the ideal solution. What is referred to as the Raoult's law. But it has as its basis the ideal solution for the liquid. So this would be Pi sat or Pi xi. These equations introduce all the C mole fractions in both the liquid and vapor phase. We also need to take into account the equations J equal to 1, Cy J equal to 1, and these equations could also be added to the equality of the fluidicities, so that there are as many equations as there are variables in the equation. So then we saw that for the Raoult pressure and tube pressure, analytically direct explicit expressions are available in calculation. So you should sort of remember them, not the actual expressions, but they can be easily obtained by simply summing over all the mole fractions that are not known. Then you will rearrange and get the Raoult pressure and the tube pressure in terms of the saturation pressures of the pure components and so on, the mole fractions and so on, the specified mole fractions and so on. So Raoult temperature is when we saw that because the temperature is not known, so Raoult temperature means, what does it mean? So it means that P and X are specified, and so I have to calculate T, that is the Raoult temperature, and also I have to calculate the mole fraction of the composition of the vapor phase. So I have to calculate that. So the equations are the same, but we saw, since I don't have known the temperature, get any explicit expression. And so we started with assuming of T naught. It may be written as X is specified, Xj, as some kind of a linear weighted average, weighted sum of the individual volume but for lack of anything else. So we need to always choose the initial guess. So this is the initial guess for the temperature. So once we have the initial guess, then I can calculate the mole fraction, because I can calculate the saturation pressure for each of the C components. So the equations for the mole fraction, which I now call as also Yi naught, that is the set of vapor mole fractions that corresponds to the temperature T naught. So Yi naught is given by Pi sat of T naught Xi by V. So we see that T naught is chosen. These are given to me. So I can certainly get an expression for Yi naught. So I got that, but however, first thing, there is no guarantee that the mole fraction constraints will be satisfied, because that's one. So the equation here, this is already specified. We assume that it has been specified with the mole fraction constraint satisfied. This is the equation that I have to verify, so I can check whether sum over if it is equal to 1 within a tolerance limit, if you want, I can put this as less than some epsilon. So it can be greater than 1 or less than 1. But if I say that it is difference from 1 up to a specified tolerance limit, because we cannot have exact numerical precision. So then, if this is there, if this is satisfied, then there is no problem at all. So we have to stop. We have to stop that means these are the mole fractions that assume temperature is the correct temperature. But invariably this won't be the case. We have to also give an algorithm for how to continue the calculation. The mole fraction constraints are not satisfied. So obviously now I have to choose the new temperature. So the new temperature should reflect the fact whether the mole fraction is added up to something greater than 1 or less than 1, just as we saw in the saturation pressure calculation, whether the pressure you calculated, whether the fugacity of the vapor and liquid, right, how they are related. The fugacity of the vapor you calculated to be greater than the fugacity of liquid according to the pressure chosen, or vice versa. Depending on it, we saw how the next pressure can be chosen in terms of the ratio of Fv over Fl. Right? In the same way, we want to take into account the fact the direction in which the mole fraction constraint has not been satisfied. So what would you do? I mean, what does it mean? Suppose, let's say let's forget about the epsilon. Let's say it's greater than 1. So what can you say about the temperature? Has it been overestimated or underestimated? It has been overestimated because Pi sat directly, I mean not directly proportional, but it is an increasing function of the temperature. So if the mole fractions were adding up to 1, that means I have chosen a higher temperature than what is required, right? So I need to reduce the summing of the mole fraction to something which is closer to 1, right? So clearly then we would have to, a good algorithm would be sum over J equal to 1 to C, while what this would do is, if this is greater than 1, right? If this is greater than 1, it would reduce, because that's what we want. Greater than 1, that means the temperature has been overestimated, and we need to reduce the temperature. So this gives a means of reducing the temperature and increasing. If on the other hand, if it is less than 1, we don't know. If it is less than 1, right, then the temperature has been underestimated, so not increase the temperature. The same algorithm will work, right? So we need to do this, and then once we have done it, right, then I can introduce, so I can simply say that I put the new temperature back into T naught and rename it as T naught and repeat the calculation, because it just goes in a loop. You just keep on doing this until the mole fraction constraint is satisfied. Once the mole fraction constraint is satisfied, all the equations are satisfied, because this is the other set of equations. We are using them to calculate the mole fraction, but temperature and mole fractions are implicitly related. So this would ensure, once the mole fraction constraint is satisfied, that this would be the case. But numerically, it has been found that this doesn't converge as quickly. So there is another algorithm which is there, split and randomness, which I will briefly discuss, which looks at a different algorithm, which in fact at least students in previous batches have said converges faster. And so you should be aware at least of this algorithm. And so you will see that when we are looking at the simple models, if you finally take it about the non-ideality in both the liquid and liquid, then you will see that irrespective of the problem, whether it's due pressure or due temperature, the algorithms will all look similar, very similar. You will easily construct the algorithm. Calculations could be difficult. But in the simpler problems, it turns out that some of the problems are easier to solve than the other. There are also different types of algorithms that are available. So since they are available and reported in the literature, you should be aware of them. Right? So in this case, we avoid the of course this remains the same, but this will be an alternate algorithm that I will discuss, which has a slightly different iterative process. So the first step is the same. Initially you have to choose somehow. Then what you do is I look at the equation EYI is equal to X is specified, so I can write this as now I sum over. So these are equations given to me. So forget about the algorithm for the moment. I can only sum over the equations. Without committing myself to what I'm going to substitute in there. And so when I sum over the equations I get is sum over so I'm not going to put any T naught or anything there. Just look at the equations, analyze the equations and just summing over them and getting a new equation for the pressure. So what this algorithm does is now divide both sides by the saturation pressure of one of the components. I can choose any one. I'll call it as the seed component. So if I now divide, you will now see why, because we understand the algorithm, then you see why it is considered to be efficient. What reasons are given in the literature. So I now divide and I can choose a particular saturation pressure. Right? Still I haven't got into the algorithm. It is perfectly valid. I have an equation A equal to B. I am dividing both sides by a same quantity that I can certainly do. Divided by, this is also PC sat. I can take it into the sum or keep it outside the sum. This is a fixed quantity. So then, what I do now so this I can write this as sum over I into 1 to C EI sand by EC sand of P xi, that is P over PC sand. Now I invert this. This P is already specified, I know that. So if I invert this, then I get PC sand of T is equal to sum over I equal to 1 to C EI sand of PC sand xi. I'm sorry, that also has to be inverted. That is denominator. PC sat by P, so this would be P divided by sum over I equal to 1 to C. So until now, we're forgetting the algorithm and just looking at these equations, adding them up, dividing by some PC sat, which is obviously also a function of the derivative. And I thought this was an exact equation once you assume the Raoult's law. No reference to the algorithm yet. Now will come the algorithm, right? So here I see that x is specified, p is specified, t is the only thing that is not specified. So what I am going to do now, or what the planners have done, is make this, because I can't calculate, p is known, xi's are known, but I can't calculate the right hand side until the temperature is chosen. I don't know it, so I have chosen it. I have chosen this. Now what about this? So I get a value for PC sat of T. Now, if the chosen temperature, so I can now get a new temperature from this. So what I will do is make this PC sat of T1, because I don't know whether that would match. The point is that if PC sat, what I get here, right? If it is equal to PC sat T naught, then again it implies that the chosen temperature is correct, but that is not going to be the same. So I make this, I find the T1 from this. So what I do is, so I make an initial guess and I calculate this quantity. So now I get an number for PC sat of T. I can invert this because we assume the Antoine's equation. So PC sat log, let's say, of T is equal to A minus B by T plus, this is another constant C. This is how it should be. Right? So now I take this and put this here, because that's the answer I'm getting for PC sat. So I can find T1 from this. Right? So I find a T1 from this equation. So once a PC sat new, so this may be looked at, this is the old PC sat. So when I've chosen T naught, I can calculate T1 sat of T naught. So there's no reason to expect that the PC sat that I am now calculating through this expression will be the same as this. Right? So I use that as a defining equation to find the new temperature. Right? So that is how the algorithm will now work. So now I find T1. Right? I find T1 from this. So I substitute this into this, and I don't invert this. It can be easily done. We will assume the Antoine's equation to be known for the substance. So I can find the corresponding T1. You can usually invert it and write this equation so that I can find the T corresponding to a saturation pressure. Right? So now I find, so all this does is help me find the T1. Now I will ask the question is, so where do we, what do we now check for? So now we check for whether T of 1 minus T of naught is less than some delta. If yes, then the algorithm stops. So we have to put it in a proper block diagram. Right? You can easily construct that. If not, no. Suppose they say the answer is no. That means the temperature I calculated, new temperature I calculated is different, quite different, away from the prescribed tolerance limit with respect to the old temperature. So if it is no, then I simply go back again. I put this T1 as the new T naught, and I go back to this equation. So the T1 that I have found becomes the T naught for the next calculation. So I will find another T1 and again check. Now the question is, when it is stopped, have we satisfied all the equations? That's what you have to check, right? So how do we check that? Now this clearly the y, right, that we seem to have not calculated at all, not looked at it at all. Right? So that is what we have to check, because we are not, what we are doing is we are getting an expression by artificially imposing the mole fraction constraint, right? And so what happens to the yi, right? So finally we can calculate the yi. So because I haven't calculated the y, so only a routine which updates the temperature. So finally what would yi be? So yi. Here.
CYI, because not these are CI.
What?
PYI becomes PI, sir. Yes, that one PI.
No, I'm summing over all the equations.
Total.
Not PI, I'm not taking the partial. Summing over all the equations. E can be taken out of the sum. So this is the algorithm. So yi is, I can either choose T0 or T1, because as far as this is satisfied, I think the two numbers will become almost equal to each other for all practical purposes. Right? So the final solution would be yi, right, is equal to Pi sat. I can choose the latest one that I have found, xi by T. Now, is the mole fraction constraint satisfied? It would be satisfied because I have found this is the way it works. Looks like it should be. There is no other. Will impose the mole fraction constraint, so it is automatically satisfied. When we got this, basically what this means is that if T0 is equal to approximately T1, that's what we are checking actually. So effectively, right, I can write this as, so once this is satisfied, right, then this becomes, I can replace this by T1 because they are within the tolerance limit. So we can see the problem is that I have imposed the mole fraction constraint, but the left hand side, we cannot say until this is satisfied, because even though I have analytically imposed the mole fraction constraint, at each stage, I cannot say that the mole fraction constraints have been satisfied, because the left hand side is evaluated at one temperature and the right hand side at another temperature. Basically, when I say T1 is formed by this, the left hand side is, if this is exactly matching, then the mole fraction constraints are satisfied. That's how I got the equation. Right? However, when you cannot say the mole fraction constraint is satisfied at this stage, when I, let's say, done the first step, because the right hand side is evaluated at T0 and the left hand side is evaluated at T1. So unless the two temperatures are matching, I cannot say the mole fraction constraint has been satisfied successfully. Because the mole fraction constraint satisfied successfully implies before I put anything that both of them should be at the same temperature. However, I know that that is not going to happen at the outset. So I use that to do the iteration for the temperature. So I choose a T0 and then I calculate this. I calculate T1. If the two are different, then certainly I cannot say the mole fraction constraint has been satisfied, because the left hand side and right hand side are evaluated two different temperatures and I haven't found a single temperature that satisfies the equation. However, once this has been accomplished, then effectively I can replace. So let's say I have reached a state because I am using the, you can also make it T2, T3 and so on, but to simplify it I am just operating between one T0 and T1. T0 is the old one, T1 is the new one. So the moment I have found this, then I come back to the equation and simply approximately replace this also by T1. So now I see that the mole fraction constraint which has been imposed is exactly satisfied to within this tolerance limit. So I say that the problem has been solved. Right? Now for the due temperature, I advise you to go back to Smith and whenever consider your own algorithm based on this idea. Based on this idea of choosing a particular PC sand and then doing it. And I think the argument that Smith and Banners have given, also I urge you to go, maybe not over the weekend, but once their quizzes are over, you can now go and look back at the Smith and Banners. What he's saying is that this is, even though PI sand is let's say PI sand depends on temperature in a certain manner. What he's saying is that this ratio is a relatively weak function of temperature, and this enables us in reaching a solution faster because the temperature differences, whereas in the earlier case you would see a lot of oscillations in the temperature before it finally converges to the previous algorithm. But this is this explanation given. I have no way of proving it, but he's saying that because we are not dealing directly with the ratio of the saturation pressures, he says that this will lead to a better algorithm or a faster algorithm. The reasoning, you have to convince yourself, but this is one of the algorithms that is reported. Similar algorithm can be constructed for the due temperature. I will let you try and see if you can work it out yourself using a similar idea of mainly choosing a. Basically, you have to get a ratio of PC to PI or PI to PC. Right? You have to choose approximately how you are going to divide by a particular saturation pressure. Are there any questions? With this we have pretty much completed the Raoult's law discussion, but for due temperature it will follow a very similar route to what I have pointed out here. So we now move to the next level of complication, right? And that would be to treat the liquid as a non-ideal solution and continuing to treat the vapor phase as ideal gas mixture. So this would be, when would this be valid? This would be low pressure, and as I said, similar substances, mixtures of similar substances, close boiling, hydrocarbons and so on, where apparently the assumption of ideal solution is valid. So now what I will do is I will retain the low pressure approximation so that I can continue to treat the gas phases and ideal gas mixture. But now I will say that I will remove this consideration. I will say I need to deal with the ethanol and water, as we have already pointed to the exhibit and acetate. So at 1 atmosphere itself, so that's a sufficiently low pressure, and we've got 1 atmosphere if we want to generate the phase diagram. I can continue to reasonably approximately treat the gas vapor phase is ideal gas mixture, but I have to account, right, for the non-ideality in the liquid. So I do that not through the equation of A, but because my starting point here is the ideal solution, I will see how to introduce the non-ideality. So we have seen two ways of introducing the non-ideality for mixtures. That depends on what your ideal substance is. So if you recollect, I wrote these two equations for the mixture. We have seen, follows from the basic definition of Gibbs coefficient, when I can write the mixture, general mixture chemical potential as the corresponding ideal gas mixture for each component plus a correction which is effectively defined to be the fugacity coefficient. Now typically, this fugacity coefficient can be obtained from an equation. It has in fact we have derived the equation now with RT by V minus dP by dNi and so on. Formula. See, that's for the fugacity coefficient effective. Right? But however, here we are not, so here the basic This would apply for the vapor phase. When we next go to treat the non-ideal in the vapor phase, this would be the appropriate equation. But here, I am treating the liquid phase as an ideal solution. For that, we defined a new quantity called the activity coefficient. It is simply defined like this, right? So gamma is defined to be exponential of mu I mix minus mu I ideal solution. So I can now write the chemical potential of the mixture, the non-ideal solution, as the ideal solution plus the gamma. So now it is possible to show that just as here, Fi mix, the analog in terms of the fugacity, can be easily shown. I have to prove it. Would be P times Z, P times Zi. This is the way of writing the in terms of the chemical potential. Here it is plus, right? So mu I ideal is plus RT of phi L. If I reframe it in terms of the fugacity, you can easily show. Have to be careful to add the mixture. So we use phi I for the pure form. Right? So it's possible to show, you can easily prove that in terms of the fugacity, it comes as a factor. You have to prove it, it's easy to prove, not that difficult. In the same way, it is possible to prove that fugacity of the mixture in terms of the ideal solution fugacity, the factor would be the gamma. So now all I have to do is this is basically the ideal solution, right? Basically the ideal solution, but the Fi is replaced by the fugacity of the ideal solution is now further simplified. Fugacity of the ideal solution further you have to again prove, because everything we express in terms of chemical potential. Prove it in terms of the fugacity requires a little bit of. We could have also defined the gammas and the other things through the fugacities, but we didn't do it. We adopted the procedure in daily to define everything in terms of chemical potential. Now converting the fugacity is quite straightforward. We should attempt to prove you are not done next, right? So this is what I have. This is basically Raoult's law, except that this is further approximated as. So we retain that approximation and arrive at what is called as the modified Raoult's law. So whenever I say modified Raoult's law, this is what it means. The vapor phase is not touched from what it is in the Raoult's law. As I have indicated here, low pressure, non-similar substances. Then the liquid phase the whole problem can be treated by continuing to treat the vapor phase as an ideal gas mixture. The liquid phase as a non-ideal solution and not as a non-ideal gas mixture. There is a big difference. Because what will happen is, this is what will enable us at least to do some calculations by hand, because the calculation of introducing the gamma will make the calculation simpler. Whereas if you were to go to the next stage of, for instance, replacing this by phi I, then you will see that the moment we get to the equation of state, the calculation becomes, volume calculations becomes important. Here the volume calculations are avoided. We will see how they are avoided. So how are the gammas calculated? Because we now need a model. We have already shown the phi I, that is the fugacity coefficient of a component and mixture, can be related to the equation of state. Right? Now the activity coefficients, which represents a deviation from the ideal solution behavior, are calculated from what are known as excess Gibbs free energy models. So we don't propose a model for gamma. Just as for phi I don't propose a model directly for phi I for any substance. Rather, I propose an equation of state for the mixture, which is different from the ideal gas mixture. Ideal gas is P equal to RT by P. This can be anything, van der Waals or anything. So that the non-ideality is taken into about not directly as a model for the fugacity coefficient, but rather as a to the equation of state. Then I relate the fugacity coefficient to the equation of state, which is our RT by B minus dB by dNi and so on, that formula. Now, again, for the liquid phase, to read the non-ideality of the liquid phase, we don't directly propose a model for gamma. It can also be done, but rather what we propose is what is called as an excess Gibbs free energy, a model for excess Gibbs free energy. It is defined as the G of the mixture minus the G of the ideal solution. We have now related that because what I have here, the gamma, is in terms of the chemical potential, the mixture and the ideal solution. Here I have again the ideal solution, but what I have here is the excess Gibbs free energy. The Gibbs free energies are coming into place. So how is the excess Gibbs free energy model means what? What is it in terms of? Right? Obviously, it is in terms of the GE is what is normally modeled. That is a specific excess Gibbs free energy. It is just dividing this by the total number of moles. It is the function of temperature, pressure in general, and the mole fraction. We need a model for this. Right? Usually, pressure dependence is neglected. So, for all practices, what will make the active decomposition model simpler? Because I simply write this as XT. It is very important to keep in mind. It can depend on temperature, and over a limited temperature range, we can even neglect that. It depends entirely on the mole fraction to a large extent. Pressure dependence is avoided. So, the disadvantage with this is that we cannot get any volumetric information because the equation states it relates the pressure to the volume. We are making use of the special properties of the liquid phase and neglecting pressure dependence of any kind. So, we cannot say anything about the volumes of the liquid phase. The specific volume, no information can be obtained. So, now the question is how is this related to gamma I? Right? So, for that, we need to again fall back on the definitions. So the best way, the logical way to proceed, obviously here the gamma I depends on the chemical potential. Now how is the chemical potential related to the Gibbs free energy? What is it that relates the chemical, what is the chemical potential also in terms of the Gibbs free energy? Also the partial molar Gibbs free energy. Right? So I automatically get an expression. So if I write GE is equal to G mix minus GIS. That's a definition actually. This is what it is excess. Because excess means what is it in excess of? I can also define quantity is in excess of the ideal gas mixture Gibbs free energy. But here, for our context, the excess Gibbs free energy means with respect to the corresponding ideal solution. So now I can write this as Xi. I will choose Xi because we are referring to the liquid phase. The mole fraction I will choose Xi. If you wanted to make it general, you can choose Zi. Right? GIEM of the mixture, the actual mixture, right? Minus GIEM of the ideal solution. Because the G, the capital G, is sum over Ni GIEM. If I divide it by N, I simply get Xi. So that's what I have written. I can now also write I equal to 1 to C. Mu I PM of the actual mixture. If you want, I can make this more transparent because I'm talking about two different mixtures. This is the actual mixture. This is the solution mixture. Now let us see what happens. So we will show that because you have an Xi. So again the motivation for how to, because we know the answers are today would be to differentiate it with respect to xi. Since I will look at, I make it j. That's how the standard results are. Because summation index I can choose anything. This is a standard practice I have followed. Whenever I want to pick a particular mole fraction, then I won't choose it as the summation index. So it's always convenient. I is the index that comes to mind. Right? So let us see what happens when I differentiate. So this is clearly a function of Tp and x. And this is also a function of Tp and x. Right? So now I'm going to differentiate with respect to a particular mole fraction, keeping the temperature and pressure fixed. So it's a partial derivative. We run out of time. So what I'm going to do is it might become complicated to work it out. So this is what will lead to the actually coefficient. What we should do is to differentiate this with respect to ni, and that's what is going to give. So I need to redo it slightly differently. So to work on this, right, and simply write this as this is what is going to work. I'll make it nj, right? Nj, and what I want to do is to differentiate this with respect to ni, keeping temperature, pressure, nj not equal to I, and it can be shown to be RT log gamma I. A good question of when we have proved it. How are we going to prove it? That's the next step. Right? So the point here I want to make is that if I relate G to the x, I can relate G to the n's, right? And then I can get the activity coefficient by using this formula. Or you can also directly differentiate the specific x's with respect to x size and get the formula. We'll see how to do that. All different ways. It is very similar now. It will be to the partial molar property. So we use many of the relations we have used it. We will take it up in the next class, which will be on Tuesday. So Monday there will be an exchange of slots, so we won't have a class. We'll be having a quiz, and then we'll meet on Tuesday. We'll take this up on Tuesday's class.